Hi all, my name is Kinuko. I work at Google as an overall tech lead for C++. Today I'm gonna talk about our recent advances for safety in C++, especially with Clang and AsiaLLVM, and also mainly about memory safety. So let me quickly recap the problem space. Memory safety has been a big problem in C++ for decades, since its beginning. Our internal analysis estimates roughly 75% of CVEs used in zero-day exploits due to memory safety vulnerabilities. This area has gotten a lot more attention in the past few years. However, this year in 2025, we still keep seeing serious CVEs coming from memory safety issues. So safety problems can take many shapes and can cause various forms of undefined behaviors. In general, safety problems that happen because of memory access outside the intended use, like intended allocations or intended time window, are called memory safety issues. At Google, we've been working on various safety problems, like spatial safety, temporal safety, initialization safety, but also for other safety issues like null pointer safety. In this talk, I'll focus on our efforts for memory safety problems, more specifically about spatial safety and temporal safety problems. Let me give another important context, which is the scale of C++ at Google. We have roughly the order of 1 billion or hundreds of millions of lines of C++ code, which is a little overwhelming, where we have roughly tens of millions of pointer declarations, where any of these could cause memory safety issues. We have roughly hundreds of thousands of production services, and nearly all of them directly or indirectly depend on C++. Safety in C++ is a difficult topic, but this scale adds another unique challenge. So at Google, we've been driving advances in memory safety, especially in bug detection area. Probably our work in sanitizers and fudging, which have allowed us to detect and fix many memory safety issues in our code and also in several open source softwares. However, we've also learned that bug detection only doesn't help us prevent new vulnerabilities from happening. And given the scale, the portion of new future vulnerabilities in our code base is actually really huge. So with these observations, our latest approach for memory safety is two-pronged. First, we try to progressively adapt memory safe languages like Rust or Safe Carbon, especially in new development wherever possible. And at the same time, we try to keep improving safety in our existing C++ code base with a stronger focus on preventing and hardening safety issues at scale, not only bug detection. And this is the topic for today. So let me start with our efforts in spatial safety, or how we retrofit the spatial safety to our existing C++ code base. So what are spatial safety violations in C++? This type of violation happens when memory is accessed outside its allocation, like your code touches an element of an array with an index that is larger than the size of the array. It's a very classic bug, but happens a lot. And based on our analysis, this type of vulnerabilities represent roughly 40% of in-the-world memory safety exploits. That is actually the largest exploitable surface. Luckily, there exists a very simple but really effective solution. That is, lifetime-bound checking. If we know the size of the buffer, which is relatively common in C++, if the code uses typical C++ container types, like std vector or a std array, then we can simply insert bound checking in a code where its elements are accessed. And such a check has existed in libc since more than 10 years. However, in 2022, friends in Apple and the other upstream contributors made a significant improvement in libc++ and made it as a more structured configuration called libc++ hardening mode, so that these checks could become suitable also for production use, not only for debug builds. However, this was actually not such a simple solution if you already have huge existing code that has never assumed having such runtime bound checking. There were a fair amount of concerns because this could make our services slower or more crashes, because this could introduce deterministic crashes in production. Although such crashes would have resulted in nastier memory corruptions if not. So in general, this should actually be beneficial, also for reliability. And runtime bound checking is actually the common approach in almost all memory-safe languages, even in performance-oriented ones like Rust. So why not? So we started with smaller steps. First, we enabled it in tests only, which revealed nearly thousands of bugs already. This convinced us that there will be more bugs lurking behind. So we stepped through enabling it in pre-prod and piloted in a small set of production services. We also conducted performance evaluations, and the results actually looked promising. So we eventually expanded this to our entire infrastructure to enable it across our critical services, like search, YouTube, Maps, etc. So each step revealed a number of new hundreds of bugs, thousands actually. And the team needed to continuously monitor production crashes for more than 3 months to fix them all. And what happened then? So to be honest, in the beginning, we were all very pessimistic. At Google, we care a lot about performance, and we thought that the bound checking would be too expensive for production deployment. However, in the end, the measurement told us that this actually cost little, only 0.3% on average across all our services. So now we look back after all happened. This was actually not that surprising between back then and now. Industry awareness has grown to have these checks more commonly in production binaries. Actually, MSBC had introduced such checks a long time ago, and others started to follow. AsiaLLVM is also used by multiple languages that have bound checking, which helped AsiaLLVM evolve further. Our data also suggests that advances in profile-guided optimization made a significant difference. And finally, Apple has driven work for performant libc++ hardening implementation. And we also contributed a performance fix upstream. So in the end, it worked out and was totally worth doing. Enabling it by default has had a big impact in security and reliability. We have an internal red team who exercises exploitable vulnerabilities across our services. And libc++ hardening has already disrupted one and would have prevented another. There was also a big reliability impact. We observed roughly 30% reduction of segmentation faults across our fleet. This was not the end, but the beginning. Standard containers in libc++ are not the only buffer types we use in C++. We work towards incorporating Apple's safe buffers proposal to eliminate, ideally, all of the dangerous pointer arithmetics by developing a tool to migrate our code automatically to use bound checkable containers. Since where buffer is declared and where it is used with pointers are different, this basically involves combining static analysis results from multiple translation units to solve distributed pointer flow graphs across all the code base. We also work on compiler-assisted bound checking where possible, and we expect to be in a much better position for spatial safety in coming years. So we had a good, promising result in spatial safety. Now I'd also like to talk about our efforts in temporal safety. So temporal safety violations happen when you touch memory after its intended time window finishes. This most typically appear as use after free when memory is accessed after it's deallocated, or wrong usage of stack variables like use after return or use after scope. This is one of the largest crash reasons in production, and the second largest cause of in-the-wild memory safety exploits in our analysis. And this has been a very common problem in C and C++ for decades. So there are a large number of research and attempts exist to date. Most approaches involve runtime cost, where the cost actually also has become significantly cheaper. However, the measurement still tells us that like a degree of the cost is at least like 5 to 10 times more expensive than bound checking. There also exist static solutions, and that has become a solid concept in Rust. It's called borrow checking. A gist of how it works is basically compiler statically checks if a variable has only either one of a single exclusive mutable reference or multiple shared immutable references, which means that like if one wants to modify a variable, all other readable or writable references need to be dropped. This sounds nice, so let's take a closer look to see what is actually needed to realize this. So we basically need, of course, a way to enforce exclusive mutability when one needs to write into a value. And we also need lifetime information at analysis boundaries so that compilers can tell how long a reference may live, even across function calls or like across different structs. Technically, it is possible to build these concepts on top of C++, and the proposals do exist. However, in reality, this requires significant design changes in existing C++ code. This is a very deep topic, and we have had lots of discussions here. But long story short, we explored a solution here that is deployable in Clang with language extensions. We started with lifetime-bound and the GSL pointer annotations. The lifetime-bound annotation has been available in Clang and also in MSBC for several years now, with a relatively good community support. The annotations can express a limited lifetime contract that is actually a strict subset of what lifetimes in Rust can tell. That is not a perfect solution at all, but we found that it can still make a non-trivial difference because such information has never been available in C++ otherwise. So what can these checks do? It can tell if an annotated parameter should live as long as the return value of the function or the constructed this object for constructor cases, and Clang can detect violations in a single statement. So for example, Clang can give a warning for these cases, like in this example, string view or std span. These view types is constructed with a temporary data, which is destroyed at the end of the statement, leaving dangling references. However, the analysis was implemented only for initialization, top-level pointer-like cases. And simple variations like these, like assignments, it's a really slight difference. Or like a nested case, like if view type is wrapped in a std optional, these cannot be caught in Clang. And we actually found that these happen really a lot in our code base. So we decided to make a series of improvements in Clang. So today, roughly after Clang 17, the analysis can also cover all these cases at compile time. Assignment case and the typical nested cases can be caught. We also extended the existing warnings like return stack address and dangling analysis with GSL pointers so that more common cases can also be caught. The first example tries to return a stack address via std span. The second one tries to push a temporary string to a vector of string view. And the last one tries to initialize a string view from a temporary string. These all have obvious errors, but these used to just compile. you need to specify appropriate warning flags. But today, they all can be caught by Clang at compile time, so that they can be avoided. And we did more. As I mentioned earlier, lifetime bound can only express a particular lifetime contract between a parameter of a function and its return value or constructed value, but cannot express more general relationships for regular functions, like where a parameter is to be referenced by this object or another parameter, which means that what the parameter points to needs to live longer than those that capture the parameter. So we propose a new annotation, lifetime capture by, to express more general referenced by or captured by relationships, so that Clang can give a warning for more general dangling cases like these. The first example tells that the parameter needs to live longer than this object. And the second one tells that one of the parameter needs to live longer than the other. The last one is a case where a parameter is actually captured by global variables. All these can be expressed with this new annotation. And of course, we deployed all of them in our code base. We have added these annotations to a set of key core libraries, like ABCL, protobuf generated code, or like our internal libraries. And we found and fixed thousands of violations across our code base, and then enabled the warning by default as an error. This means that in addition to fixing existing violations, it prevents the same type of violations from running forever because they can't compile. The deployment process was similar to that of libc hardening. However, enforcing warnings was much easier. All breakages happen at compile time and never need to hit production. This is much easier, So debugging and fixing violations was very easy. As an end result, we had another observable impact in bug reduction and reliability. This reduced roughly 1/3 of use after scope errors in tests and roughly 17% of use after freeze in production. In our data, this also keeps surfacing hundreds of warnings per week in IDE, preventing many future use after freeze from running. We also saw roughly 20% of drop in unique crashing workloads with segmentation faults, which means that we had another big impact in reliability. As a next step, we are proposing to implement a new analysis that performs CFG-based flow-sensitive analysis so that it can catch violations across statements, finally. The basic design is inspired by a borrow-checking model for Rust. In short, it performs a form of points-to analysis where we track a set of loans or borrowings issued to a possible source of a pointer variable, and check if a loan is valid or expired across control flow. This new model can express more advanced lifetime relations even beyond the current annotation syntax. And we believe that this will make it easier to extend the annotation in the future, maybe to a more expressive one, like Rust-like lifetime annotations. You can find our RFC on Discourse, and we'd love to hear community's thoughts there. So wrapping up, I talked about our efforts trying to advance safety with unsafe reality of tons of C++ code. We've adapted and retrofitted learnings from memory-safe languages like default-enabled bound checking for spatial safety and lifetime information and analysis for temporal safety. We've surfaced and fixed thousands of existing violations and keep preventing them from happening. These approaches also have had an observable impact in reliability, and it showed security effectiveness with actual internal offenses. We have several more ongoing work, as I mentioned, and we hope to be able to report back all the results to the community soon again. So you can find RFCs and pointers I've mentioned in this talk on Discourse. I think the slide deck will be also shared. The work I've mentioned was not done by a single person, of course not, but by a set of active contributors with help from the community, and they are not only from Google. I'd like to give a big thanks to everyone who was involved in this effort. So that's all.
Any questions?
Yeah, thank you for a great talk. I just want to ask, C++ lifetime is very it's runtime property, and that is different from the Rust lifetime. That is very static concept, and I'm wondering how to handle like std move in the temporal safety checking. Like std move can move the ownership of value to the other value. So how to analyze that and the existing approach and in the future approach. So doesn't make sense. Sorry.
Yeah, thanks. I think like C++ lifetime could look more dynamic just because objects in C++ are shared across like many code. Multiple code pointers can modify the data. Therefore, like we often need global knowledge to be able to precisely know like how long one of the reference needs to live. However, like if we apply like the learnings from Rust, basically like if we can restrict the code to be able to have only single writer at a time, that is basically like exclusive mutability, which makes the analysis service much simpler. And with that, and also like lifetime information, complete lifetime information available at all the analysis boundaries, we believe that it should be possible to statically analyze everything. Student move can be also like statically analyzed, but the difficulty is that like doing so will need to really change the design of existing C++ code, which is not possible in reality. So we are like ending up doing opportunistic bug finding. And back to the question of like how we do handle like for example student move cases. Again, like in local context, we can analyze that. How that same reference might be used in different contexts, which cannot be restricted if we don't have exclusion mutability. That's a problem. Does that explain?
Any other questions?
Yeah, thank you for this interesting talk. I have actually a more general question, and I would like to ask, how do you see the future of C++? I mean, considering all of this work going in hardening the language, all of these problems about safety, I'm really interested. I mean, you at Google, would you advise someone to start a project with C++ from scratch, or would you say no, better use Rust? Or could you say something about this?
Okay. With a caveat, like I can't really speak for Google, but like I can give the thoughts that like we are discussing with our group. So for new projects, we actually don't want to advise, like recommend using C++. However, in reality, we have like tons of software ecosystem which is only available in C++. So the feasibility needs to be actually like weighed. Is it possible to write it in Rust? If so, we definitely, Rust like in other like memory safe language, we definitely recommend. But if it needs to rely on existing C++, we still like need to let them use C++. Therefore, all these work is still needed. And for future of C++ safety, I have both very optimistic view and also kind of pessimistic view. I know the reality is that like even with all these efforts, the safety gap between C++ and other memory safety languages is still really huge. we have many numbers that show that. So I think like, I have all these work could make a really significant progress, and it's amazing. Like we still keep making progress, after the long decades, but we will not be able to close the gap. That's my feeling.
My question is going to be easier. Thanks for the talk. For libc++ hardening, just curious, what mode are you guys using for production?
I think it's one of the relatively lightweight mode. I forgot the exact name, but like we don't enable, for example, bounded iterator or like some of the heavier ones, but we just like enable like optional like out of bounds access in element without objective.
I have a question about the lifetime capture by X and the intraproduce analyze. So it looks like the intraproduce analyze can overall cover the lifetime annotation. So why we need those two things, and what's the relationship between those? Since if we can have an intraproduce analyze, we can analyze the capture, right? So then we don't need to annotate it manually.
So you mean that like lifetime capture by and
yes, and you mentioned the intraproduce analyzer.
Oh yes.
Yeah.
So for the intraprocedural analysis is basically like to enhance the analysis scope for existing annotations, like lifetime capture by or lifetime bound, so that we use the same annotations, but like we improve the internal analysis engine, so that we can catch more violations using the same annotation.
All right, I know there's a few more questions, but we've run out of time for this Q&A, so if we get some time to connect and ask questions later. So let's give her another round of applause.